Today in this video, we'll talk a little bit more about relatively weak signals. As you know, the stretching vibrations come all over the place, and the bending vibration starts around 1450 with a CH, one of the highest frequency bending vibrations. The corresponding peaks of the stretchings will be around 3000, right? So here, this area is called fingerprint region, where the bending vibration is showing up with a medium to small size usually, and some of the stretching also comes this area with a weak intensity. The CHs and CC double bond and the single bond, they are a weak signal, and also triple bond as well sometimes. And the CHs stretchings are coming around 3000, then triple bond around 2200, then double bond of carbon come around 1600 to 1400, and single bonds are falling into this area with a small or medium size. They can be easily confused by bending in this area, but even other area. And the SP3CHs, they normally come in with multiple signals, so their intensity becomes stronger than expected, so you don't miss them. However, because the peak looks big and too many signals coming together, we normally ignore the details. So today here we're going to look into some of those peaks, because the OHs and NHs giving intense peak in this region, right? 3000 to 4000, and the carboxylic acid OH even come across the 3000, enter the 2000 region. And then CO double bonds and CO single bonds and other heteroatom also showing intense signal in bending vibration area, so no problem to read them. But the one with the carbon hydrogen is troublesome. But you should know you have an NMR, HNMR, to read those signals in detail. And the carbon 13 NMR also will give you more specific information about carbon related functional group, or alkane, alkene, alkyne. Nevertheless, it's good to know about some more details of those carbon hydrogen related peaks on the IR. So let's talk about that a little bit. So this is the typical zoom in of the SP3CHs. And these two peaks at upper 2900, upper 2800, those are from the methyl groups. This is the asymmetric stretchings of methyl group. This one, upper 2800, is usually symmetric stretching peak of methyl group. And their vibration mode is like for symmetric. First, all the bonds are stretching out together and then stretching back in together. Okay, that mode is giving somewhat less frequency because it's a little bit easier. And here, when you have this one stretching out, other two stretching in, and when this comes back and these are stretching out, that kind of a stretching vibration, the asymmetric stretching vibration is giving 29, upper 2900. Then the remaining two here and here, they are caused by CH2s. This one here is about 29, 26, so the bottom lower 2900. This one here, it's not quite low, but kind of bottom 2800. Okay, so 29 top, 29 bottom, 28 top, 29 bottom. Two tops, 28, 29 and 28 is from the methyl group, somewhat lower, okay, for methylene groups. So the asymmetric stretching of methylene is happening sort of the way I described earlier with the methyl group. One stretching out, the other one stretching in, and then reverse. The process keeps going on. That shows a little higher frequency than the stretching symmetrical one. Okay, even that was the case for methyl group, symmetric, asymmetric. And then for comparison, methyl groups asymmetric is a bit higher than methylene asymmetric stretching. Then symmetrics are lower than methyl symmetric stretchings, a little higher than the methylene stretching, symmetrical stretching. Then you have all of these bending vibrations, right? One of the highest one is a scissoring. That's when you have these two methylene hydrogens are scissoring, come together in, come out together, scissoring. That happen to have a most greatest decay value. As you can see, you have to come close with the electron. Then when you go out, you are getting closer to the electrons. So the K value is big. But wagging is when you have these two together, coming out of the page, meaning approaching this electron and going in, approaching this electron, and they don't change their angle, but they're just approaching this side, the other side. So that's kind of also expected some repulsions. So somewhat less than this, but high end of frequency. Then twisting is a little easier because here you have when this hydrogen coming closer to this part, the other one getting closer to the other. So it's twisting, okay? So it's like this. So when you do that, it's getting closer to the other pair of electrons, but they are going away from each other. So it's a bit more easier. And as you can see, the rocking is way below. That's because they are moving this way. They are moving away from these electrons. At the same time, they are coming to this. So it's not that difficult. So when you have structure like this or this, you have methyl groups and you have a methylene groups. So you expect all of these with this additional peak, right? And then intensity for methyl related peaks will increase as you have a more concentration, more number of methyl group. If you have more methylene, as you make the chain longer, right, there are more methylene, then the methylene related peak size will increase. So the shape changes. That's what you can expect. But say you have a structure like this, you have no more methyl related peaks, so this and this will disappear. Therefore the signal will be simplified like something like this, and this one at the lower end of the 2900 and then lower end of the 2800, And if you happen to have some attachment, like I don't know, OH or something, then you have CH, then there could be some additional small peak here or here, you know. So you can expect the shape change around 29 to 2800 range for sp3ch. Then we know when we have sp2 carbon, alkene for example, you could have a cis isomer and a trans isomer. And as you know, there is a dipole coming from sp3 carbon to the sp2 carbon. So overall, the cis molecule is more polar. So the signal for CC double bond and CH stretching will be more intense. So you are expecting the sp2 carbon hydrogen stretching comes above 3000, and it can be add up to this. Sometimes it's a pretty close and pretty intense. It becomes like shoulder, and then this is a little more than 3000 it happened to be. And other cases you may see them as a separate little peaks, sharp, you know, depends. Also, the double bond gives a signal around 1600, little above 1600. I want to say it could be even 1650, and somewhat you know, visible size of the double bond peak for cis isomer. But when you have trans isomer, when molecule, the reduced mass is somewhat bigger, then the frequency decrease a bit. So when that happened to be shoulder of this sp3, it could be somewhat smaller. Or when it's a small piece of the double bond, then it could be isolated peak, but compared to cis isomer, trans isomers intensity can be smaller. And the double bond, carbon-carbon double bond stretching also can be sometimes almost like this size for trans. Okay, so trans, cis, carbon-carbon alkene double bond, and that for sp2 carbon H stretchings here. Also, there is a bending vibration for these hydrogens. Whether the H is in this way or you know, one here, one there, either case, there could be two typical modes that gives you dipole moment change, because IR is detecting basically the dipole moment change while the vibration is taking place. So taking this example, when you have two hydrogens scissoring, like this case, in plane vibration, the frequency can be similar to the scissoring here, about 1400, but the dipole moment is much greater than this case because carbon here is more electronegative. So normally the intensity and the broadness is much greater with the double bonded hydrogen. If I have to show you, right, the scissoring case 1451 can be medium size but normally sharp. No, that's for CH2 sp3, right? Scissoring. But then you may see for in plane bending vibration of the double bond, much more intense and broad. Okay, it could be. So double bonded ones, same CH2 though. Also, something like rocking or twisting or wagging, the sp2 carbon has a no steric hindrance, right? You have the third hydrogen missing. So when these are moving out of the plane, there is empty space. So repulsion, you can imagine, is much less. So K value is much smaller. So it usually come around 1000 to 680. And intensity wise also, this, I mean, they can be pretty broad and intense, you know. Probably you can compare it to the CO bond or even more broad. Then we have triple bond. I believe I talked about this, but if you have alkyne, the alkyne that's embedded in the middle of the chain usually shows a smaller peak at 2200. But the one that's asymmetric has more dipole moment, so much bigger. It could be quite big, okay? Usually the symmetric one or the middle one is tiny, barely detectable, but this kind is as big as medium size. And if you happen to have a more polarization with the resonance or having some electronegative atom nearby, that causes the polarization as well. So the signal, the peak, can be very intense. That means the CH also can show up around this area, but somewhat bigger. I wouldn't pay attention to the number too much as far as it's bigger than 3000 reciprocal centimeter frequency. But intensity wise, this can be quite bigger than those of the sp2. Then, since you have one hydrogen, the bending vibration of the alkyne, there is not so difficulties to bend, right? But there is no scissoring. It's all same whether you go on the plane this way or you go up and down. It's anyway same bending vibration with a very small K value. So normally the bending vibration of the CH comes in the very small number, like a 600, okay? 600 something bending. And surprisingly very fat and big, like these. And you can easily get confused with the CBR or CCL kind of size and fatness of the peak. All right, now let's talk about aromatics. You know, multiple times you will find the difficulties to tell apart these aromatic signals from the alkene signals. So generally though, you get more sp2ch stretching signals for aromatics, and also you find more modes of vibrations for carbon-carbon double bond around 1600. And there are some typical stretching and bending vibration modes of aromatics, depends on their isomers. So if you know those numbers and modes, it will be convenient for you to figure out whether you have aromatic or you can even figure out whether the aromatic has ortho isomer or meta or para, even mono substitution, and tri and mo, and so on. Here I have these hydrogens are stretching all out together and then going in, out, in, that stretching, symmetric stretching. That is so-called in group theory and spectroscopy purpose. We label the symmetry as a A1G. But important thing for you guys is the number. It's coming at around 3121. Then there are about 5 more CH stretchings, and these two belongs to the E1U symmetry, and those belongs to E2G symmetry, and that belongs to the B2U symmetry. And as you can see, hydrogen stretching out, stretching in, and coming back, going out, while other hydrogens are not moving. Here in opposite, 2 are not moving, but 2 of the 4 moving in, and also other 2 moving out. Sort of they're similar, right? In a way, if you add them up, right? Dipole moment going this way and that way, it's about the same, but that's happening on different carbon. We use this symmetry for orbital when you talk about the molecular orbital energy level of benzene, a similar way. But anyway, we don't want to go through these details of the symmetry now, but you find this many CH stretching modes, okay, and the numbers are quite similar, slightly over 3000. So they are all, merged up with the sp3 CHs, as you saw before. You have couple signal, and then couple signal, stretching, symmetric, asymmetric stretchings of sp3, but that's around 3000. So here is the 3000. Then these things come just like the sp2ch of alkene. Many of them can show up. It can show like many shoulders, okay, and they are all these. Depends on what you have. Some of the peaks becomes more polar, so more intense. So the spikes can change, like a small but big here and small and big there. Depends on what you have. Then there will be vibrations of carbons of the double bonded benzene ring. And I'm not gonna go over these over 20 different modes. I mean, literally more than 20 vibrations possible. But I'm gonna pick just a couple to address the point here. So I didn't list all 20 something vibrations of the ring, but these out of the 4, I showed these 2 double bond vibration modes that are relatively visible, because those 2 numbers are greater than 1450, where the bending vibrations of other CHs and everything else starts. So we normally use them to say you have benzene ring. Compared to the regular alkene that doesn't have any resonance or anything, the numbers seems to be a little lower, because normal alkene was around 1650-ish. And the aromatic rings, their double bond stretchings are, relatively a smaller number, and those are the ones that's bigger than 1450 in terms of frequency. So as you can see, 2 carbon here and 2 carbon there, they're getting stretched and shrink this way. As they do that, the hydrogens are moving opposite direction, okay? As they move away, the hydrogens getting closer, and as they come close, hydrogens spread apart, and that's what they do, and that's the stretching of the double bond. 1612 for the aromatic ring. And there, when 2 carbons are going this way, those 2 who did not move right now going this way, and other hydrogens are going up, canceling their motion out. So That's a bit easier turned out. So 1477. There are many of these, about 6 of these or more, depends on symmetry. But now you have a bending vibration mode of the ring, not just the hydrogens here, like you saw. Also, these are the stretching. I'm sorry. So here, all the bendings. So what happens is these carbons and hydrogens. There are many ways of having, such as when these carbons are going up and up, these are going down. While these are up and up, they're going down, 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 and up, up, and different combinations. But either way, you can see that these hydrogens are, scissoring kind of thing. And you saw before, scissoring of CH2 of the double bond was difficult. And these are corresponding to the out of plane motion, raggings, right? So they are much easier. So, and I hope you see those two different groups near 16 to 1450, multiple of them, and then some of the bending vibration that gives you also very intense signal, like the case of the alkene, regular alkene. All right, so these are the 4 4 compounds with 3 isomers: mono-substituted benzene, di-substituted benzene, ortho, meta, para isomers. And this area 3000, right? You have sp3 3000, little less for CH3s. Okay, CH3, no CH2 in this case, but you can have it if you change the R group. But the point is, you are expecting sp2CH here, and it could be a couple more, depends on how polar group you get, right? So it's gonna happen always here, here, here as well. I didn't put them there because of the space. And also another thing you can have is around 1800, you can have overtone here as well. I mean, every case. And their shapes come in different shapes, but I'm not gonna talk about that. So these are the common things, okay? The different things happening at this double bond area and the bending vibration out of plane area, okay, below 900 something, so below 1000 basically. And they're not weak or medium size, they're all intense. So the double bond that you can see, the 1600 one, remember the 2 double bonds of the ring going in and out while the hydrogens are going opposite way, right? That one is weak. But other double bond stretchings are stronger at above 1450. So basically those 2 I showed you before. Relatively 1610 is weaker for mono, okay? Then ortho di-substituted one, it's much weak, almost gone, okay? And these are relatively stronger compared to that, even when you compare to the mono. And then out of plane here you had 700 and a little above 700, and you have only 1. So almost like when you have a dye substituted, spectrum becomes simpler with the 1600 small. Okay, that's what you need to, how you need to remember maybe. Also for symmetrical para, about same thing happens. 1620, the stretching mode of the ring is becoming less because it's not as a polar, basically, right? Why they're not intense? Because molecule is relatively more polar, and that mode of this motion it's not changing polarity as much. Also, the outer plane around 700, 800, they are simpler, 1. Okay? And the mono and the meta, they are the one more complex, especially the meta dye-substituted one. As you can see, 1620 is very intense. And you have a couple peaks and a couple more peaks. I mean, I said total 6 or more stretchings are there, and you only see 4, so you expect a couple more. And they can fall into the, they are in the bending vibration mode area, 1450 and below, so you may not notice. But when you have a big electronegative or resonance group, then the molecule becomes polar and they can grow out of the bending vibration, then you may notice more than 4. But anyway, those two are extinctive one, usually even with the nonpolar groups. So you want to remember based on these two. So I hope you see the pattern. Okay, so symmetric one, weak. And then mono and the meta, strong. And then even for the outer plane, the meta has many peaks, over even 800. Okay, so meta, easy to remember. Ortho and the para, outer plane, 1. Mono is slightly in the middle of these two and the meta. So if I get more requests from students, I will probably go into a little more in depth, but otherwise this should be enough for sophomore organic chemistry. So